Welcome to my new calculus channel. My name is John Gabriel. And in today's video, I'm going to talk about what are differentials again. And this is the second video that I'll be discussing the topic. So if you're wondering what happened in the first, I recommend that you watch that video, which is also available on my YouTube. Well, let's begin. So before we continue, if you go to my new calculus site, you will see that you can have access to all these resources. Yeah, one are the articles, interactive dynamic applets, and also this 10-lesson new calculus course in which I explain in 2 lessons quite a lot of information about differentials. So I'm going to look at one of those today, and that one is lesson 5, what are differentials, okay? So before I do that, I want to tell you that you can also download my free ebook, which is available right here, An Introduction to the Single Variable New Calculus. This is the most important mathematics book ever written in the history of humans. And it contains all the basics of the new calculus and also exposes all the fallacies and ignorance of mainstream academia with respect to mathematics. So, and in addition to the 13 chapters in the book, I produced 13 videos in which I explain each of those chapters individually. So this is a good place where you can go to and watch those videos. So in any case, let's begin now with today's video. So I discussed differentials in the previous video. And so the new calculus derivative is defined by this expression here, okay? So by the way, a lot of you don't actually know what these things are because you tend to just skip over things and not really pay attention to details. So very quickly, I'll show you what this means, okay? So really, if you have a graph like that, okay, and you have a tangent line here, let's say you have a tangent line there, like that, okay, at that point, then m is this distance here, and n is this distance, okay, from the point of tangent. They're horizontal distances. So don't be mistaken, by the way, in thinking that m and n are equal. In some cases, they might be equal, for example, in the case of x squared, which is an even function. But in any case, they are related, and they're also related to the point of tangency, x, right? So all these 3 here are related in this formula. Now, this definition here can also be written as you see here, okay, using the Leibnizian differentials. So now, what is a differential, as you can see from this formula? All it is a finite difference, okay? See this little expression here? It's a finite difference, all right? It's a difference of this ordinate and this ordinate. That's all it is. And likewise, dx is equal to this or any multiple of this. So for example, if you had dy dx is equal to 3/4, like that, then it will also be true that it's equal to 3/k divided by 4/k, where k is any other number, okay? And similarly, it will also be equal to 3 plus 3/4 plus 4, and so on, okay? Right, so this here is not an ultimate ratio, as you've often heard. There's nothing about infinitesimals or anything like that. That's just nonsense. An infinitesimal doesn't exist any more than infinity exists. And there is no rigorous formulation. Back in the 1960s, and most of you were not born at this time, there was a certain mainstream academic called Abraham Robinson, and he wrote something that most will recall as non-standard analysis, where supposedly he put infinitesimals on a rigorous footing. Nothing could be further from the truth. In fact, even as you know, mainstream calculus itself is flawed because there is no systematic way to find the derivative. All you have is the first principles method, and it's flawed because you need to know the derivative in order to find it. Remember, I showed you in past videos that this definition here, as you see it, let's just write it down quickly. F of x plus h minus f of x over h is actually, according to the mainstream, defined by this, okay? It's defined by this. F of x minus L less than epsilon. Now, this h can also be seen as delta, but they're the same thing. H and delta here are the same thing. So this definition here requires that you know L, but guess what? L is equal to the derivative. So not only is it circular, but it's flawed in many other ways, because in the first principle method, H is for some time non-zero, and then right at the end, to complete the limit, H must be zero, okay? Because what you end up is something like this, right? Plus lim q of xh, where h approaches zero, right? So if you've got this expression here, h has to be zero. Otherwise, this side here is never equal to this side. Do you get it? Okay, because this here is the derivative, and this here is the expression in x and h. So very well. Now, as you've seen, dy and dx are finite differences or differentials, and a ratio of differentials, as you see here, okay, as you see here, is called a derivative, all right? And you can use them exactly as you would numbers, because they are numbers, except that they can take on innumerably many values, as I've shown you here, okay? I mean, as long as this fraction here is proportional to or equal to any other fraction, then you can find many equivalent fractions. But that doesn't change the fact that dy and dx are numbers. They're symbolic numbers. And I think I've shown this to you before in this video. So you see dy and dx here are, in this applet, I mean, dy dx are differentials. See, dy is just the distance between the y ordinates, and dx the distance between the x or the abscissa. So it doesn't matter how you move these, the slope of the tangent line will remain unchanged. And if you take a different tangent, let's just bring this closer, take a different tangent like that, then again, the same story. This slope here will not change, okay? So you'll have the differentials, which can be any equivalent fraction. And so you have the derivative, which is just a ratio of differentials. All right, let's dismiss this. And so we'll look at lesson 5. And in lesson 5, as you can see, dy is equal to f of x plus n minus f of x minus m, and dx is equal to m plus n. So both of these are called symbolic differentials. And instead of working with variables of constant separately, and perhaps one at a time, we are in effect working with an entire expression as a whole. So in this case, the expressions of finite differences in y and x. So as we can see here now, let's suppose that f of x is equal to x squared and dy dx is equal to 3/4, okay? What this means is that if we had dy dx is equal to 2x, this will imply that dy is equal to 2x dx. Yes, you can actually multiply it, as you see here, because dx is a finite difference, just like dy. So they're not infinitesimals, okay? And you can multiply it like this. And then according to the new calculus, in which the definition is well formed, the differentials dy is equal to 3 and dx is equal to 4. And by the way, those are not the only ones, as I showed you. There are many. We can, provided we can find x, m, and n such that 3 is equal to this, and 2x times m plus n is equal to 2x times 4, then we are done. And in lesson 5, I'll show you how to do this, okay? So you can go through this entire process here and then equate m in terms of n so that you can find both an n and an m. Now remember, in the new calculus, you do not have derivatives at point of inflections because there is no tangent line possible there. You only have half tangent lines. And a half tangent line is not sufficient. So this criteria must hold for all tangent lines, not just for some and not for others. So there is consistency in the new calculus, okay, unlike the bogus mainstream formulation, where in some cases it may be possible to find a gradient and in other cases not. So, and similarly, if you have a second order differential like d squared y, this doesn't mean dy squared, it just means a second order differential, which is shown as you see here, f prime of x plus n minus f prime of x minus n, then you can also do the same thing here. And provided you can show this is true and find an m and n, and then you can show that the second order derivative is true, since m plus m is 4 and dx squared is 4. But that's not dx squared again, it's a second order differential. So now, if this is the first time you've seen these things, it takes a while to get used to it because this has never been taught in mainstream mathematics. So you'd have to study the new calculus and learn how to do it, okay? And so in lesson 5, I give you several examples. And if you go to my website, you will see there's also a lesson 6, which talks more about differentials, and you'll see a lot about the meaning and how to manipulate them in more complicated ways. So I hope you've enjoyed this little presentation, and I'm thinking I might produce the third part if I've left out anything, but if I haven't, well, this will be pretty much it. Please subscribe to my channel, spread the news, and if you have any comments or questions, go ahead and post them. Please, not more than 1 or 2 questions at most. And I'm not interested in a long essay, so keep your comments short. Well, my name is John Gabriel, and this is a New Calculus channel. Till next time, goodbye.